This is the lesson for 4.7 in pre-calculus, and this is some really, really good stuff. We're going to be doing some story problems where we're going to get functions in two variables, and we want to work on writing those functions in terms of only one variable so we can do things like find extrema and such. So, an important concern of mathematics is finding the minimum or maximum value of a function. You have already seen quadratic and cubic examples that involve minimizing costs and maximizing profits. Other such applications use mathematics to minimize the structural stress on a girder or to maximize the volume of a container made from a given amount of material. Pretty common problems in the engineering and business worlds. Minimum and maximum values are often referred to as, well, minimum or maximum. Those are both extreme. So, extreme values. Approximate extreme values of a function can be found using a calculator. Exact extreme values are most often found using calculus. Whether technology or calculus is used, we always need to write a rule for the function to be minimized or maximized. If the rule depends on two or more variables, then we also need to find a relationship among the variables so that the function can be written in terms of only one variable. Finding that relationship is key. Developing these skills is the goal of today's lesson. This is going to be fun. All right, so title your notebook 4.7, Forming Functions from Verbal Descriptions. And the objective will be to form a function of one variable from a verbal description and, when appropriate, to determine the minimum or maximum value of the function. Okay, so again, great notes, but write these notes with understanding. And when we're in class, make sure you're asking questions. So, an open top box with a square base. You all know me. As soon as I start reading a story problem, I'm going to draw a diagram. So, an open top box with a square base. Well, picture a rectangular prism with a square base, which I would draw just like this, is to be constructed from sheet metal in such a way that the completed box is made from 2 square meters of sheet metal. So let's put in the dimensions of our rectangular prism or our open top box, and I'm going to call the base W by W and the height I'm going to call H. And I have 2 square meters of sheet metal to make this open top box. All right, so the easiest way to visualize what I'm going to do is to draw a net of this rectangular prism. And you guys did that at the middle school. That means we're going to take this thing and we're going to clip along the edges of the lateral faces, and we're going to fold this thing down into a two-dimensional diagram. So the easiest thing to do would be picture the square base that is W by W. There it is. And now if I fold those lateral faces down, those would all be congruent rectangles, just like that. And one dimension would be W, the other dimension would be height. So I see, as you see I started up here, the base has an area of W squared, and the 4 lateral faces have an area of WH. So I'm going to go for WH. And what does that equal? Well, it has to equal the 2 square meters of sheet metal that I have. So that equals 2. Now, this is what we call a secondary equation right here. All right, because we're talking about volume, all right? And this is a surface area equation right there. That's a secondary equation. But now I can use that secondary equation to write my volume function in terms of only one variable. So let's go back to geometry now and talk about volume of a rectangular prism. And that's going to be volume in terms of my base W by W and my height H. And you remember again from geometry, the volume of any solid is area of the base times the height. And this is going to be my primary equation right here because I need to express the volume. Okay, so, well, volume then. What's the area of the base? Well, the base is a square of dimensions w by w, so the area of a square would be w squared. Okay, times the height, well, that's just my h. And there's my volume formula in terms of w and h. Unfortunately, I have to write that in terms of only one variable. So I go up and I look at my secondary equation up here. And would it be easier to solve for w or for h? Well, I think I could easily solve for this h right here. So let's solve for h. So let's see, 4wh would equal, let's subtract the w squared, so 2 minus w squared. And then I'd have to divide by 4w on both sides to get h equals 2 minus w squared over that 4 times w. And there is h in terms of w right there. Okay? And I don't think I can simplify that at all. But what we can do now is plug that into our volume formula. So now I have the tools to write volume in terms of only h. So, oh, excuse me, I'm going to write this in terms of w. Okay, so v of w equals, okay, and what do I have? I have the w squared right there. And then h, but I'm going to write h as the quantity 2 minus w squared over 4w. Just like that. Now this I can simplify. So I'm going to cancel out one factor of w in the numerator and the denominator. And then I could probably distribute that w to the 2 and the negative w squared. So I'm going to say v of w equals, well, let's go 2 times w minus w cubed over 4. And I now have volume in terms of the width of the base of that open top box. And that, my friends, is what engineers do. Okay. Math rules, that's right. So, graph V on an appropriate window and find the width and height that maximizes the volume. All right, that's great. Okay, so, well, we're going to use technology to do this graph. But on an appropriate window, that means we need a real domain. Okay? Appropriate window, the real domain. And let's go back to our net. And remember the base was w by w? So let's do a double inequality in terms of the width of that base. So do you all agree that this w, to make an open top box, would have to be bigger than 0? So let's say 0 is less than w. And remember, we had 2 square meters of sheet metal to work with. Okay, so that means one side would have to be less than the square root of 2, because the square root of 2 times the square root of 2 would give me 2. And that would be all my metal, and I'd have no lateral faces. So 0 is less than w, and w is less than root 2. Okay, now you go to your calculator, okay? And what you're going to do is you're going to put this function in as y sub 1, and then you're going to go to your window, and you're going to go the x interval on your calculator from 0 to root 2. Okay, now there's my picture, but let me get out the calculator so I can talk you through this. And we'll do this together in the classroom as well, assuming I can find my graphing calculator. Ah, here it is right here. Okay, so now I'm going to go to my y equals and clear anything I have. And now I'm going to write volume as y sub 1, and then I'm going to put that 2w minus w cubed over 4, but I'm going to have to use x's. And be careful, you have to group the 2w minus w cubed. So I'm going to go parenthesis 2x minus x to the third power, close my parenthesis, and then divide by 4. All right, Now, let's use our W interval here, 0 to root 2, but I'm going to go to the window button on my calculator, and I'm going to make my x min 0 and my x max root 2, second root 2. Now, I'm not going to worry about x scale. That's okay. All right? And then, instead of thinking about my y's, you know what? I'm just going to do a zoom fit. Zoom 0. And here comes my graph on my calculator. And if I do the graph on my PowerPoint, I wish you could see my calculator right now, but those graphs are identical and they are perfect. So now, we need to find the W and the H that's going to maximize our volume. So you know that this point right here, the extrema of this graph, the X would be my W and the Y would be my volume. So we know how to find extreme on our calculator. We're going to go second calc, maximum, which is number 4. And then my calculator says left bound. I'm going to hit enter. My calculator says right bound. I'm going to hit enter again. And then my calculator says guess, and I will hit enter again. And I am getting, let's see if I have the same thing on my PowerPoint. X equals 0.81649,881. Well, on my calculator, I have 0.8164957, but different windows and stuff. That's approximately the same number. And my Y is 0.272165553, and on my calculator, I have 0.272165553. That one's perfect. All right, so let's put that to work. So W is going to be approximately this 0.8 right here. And I put it a little farther right there, but watch what I put in my diagram. Okay, so I'm going to call this dimension right here approximately 0.8 and 0.8, and now all I need is my height right here. And look what I have. Remember earlier, didn't we have W and H in an equation? So H is approximately, and remember our H of W was, okay, previous slide, 2 minus W squared over 4W. All right, so all I'm going to do is take this and change my W's to 0.8. So let's punch this out on our main window. So I'm going to go parenthesis 2 minus 0.8 squared, close my parenthesis, divided by, and now put this 4 times 0.8 in parenthesis too. Parenthesis 4 times 0.8. All right, 2 minus 0.8 squared, quantity, divided by 4 times 0.8. I think that's going to give it to me. And I'm getting a 0.425. So let's see what I rounded that to. Okay, oh, let's see. So let's see what happened here. Oh, you know what I did? On my calculator, I put in that for my W, or when I did the PowerPoint, but when I did this, I just did my 0.8 right there. So let's see if I round this to approximately 0.4, which I did, and that's what my calculator just gave me, 0.425. So graph V on an appropriate window, we see that right here, and find the width and height that maximizes the volume. Well, we're going to say the width needs to be approximately 0.8 meters, and the height needs to be approximately 0.4 meters. So this diagram is not to scale, obviously, but that's okay as long as I have my dimensions in there. Okay, and remember, this is my width and this is my volume. So what's the maximum volume? Approximately 0.27. Okay, next problem. A north-south bridle path intersects an east-west river at point 0. So it looks like a hyperlink, so I bet you I'm doing the diagram on the next slide. Let's see. Yeah, here's my north-south bridle path. And guess what? East-west river. East-west river. And the path and the river intersect at point 0 right there. Okay, what else are they going to tell me here? At noon, a horse and rider leave O, traveling north at 12 kilometers per hour. So let's go back to our diagram. And this horse is traveling north at 12 kilometers per hour. So the distance that this horse has traveled north, I'm going to call that 12 times the number of hours, or H is 12t. Now, what's the boat doing? Well, at the same time a boat is 25 kilometers east of O. So let's go out here to the east, 25 kilometers. Uh-oh, didn't mean to hit that. Let's get back there. There it is, and that's 25 kilometers. So the boat is here, and I think the boat was traveling west. And how fast was that boat traveling? Let's go back and look. 16 kilometers per hour. So this distance west would be 16t. Now, what am I going to do? What kind of geometric model am I going to do to figure out at any time how far is the horse from the boat? Well, let's think about this. Let's go read the problem. Make sure we have everything here. Express the distance d between the horse and the boat as a function of the time t in hours afternoon. We're there. So isn't that distance going to be the hypotenuse of a right triangle right there? Okay. And let's do, how do we solve a right triangle? We use Pythagorean theorem. So this distance right here, I'm going to call b right now, and we'll write that in terms of t in just a moment. So do you guys agree that right now h squared plus b squared would have to equal d squared? What's that b? Well, if this distance was 25 kilometers and I've traveled 16t to the west, wouldn't that b be 25 minus 16t? There it is. And now, by Pythagorean theorem, we know that what? Well, my distance squared has to equal my height squared plus my base squared of that right triangle. Okay? And now let's write both h and b in terms of t. So that means distance squared is going to be, well, what's my height? 12t squared. And what's my base? 25 minus 16t quantity squared. There you go. Okay. Now, solve for d. So we're going to have to take the square root of both sides. We've got to get rid of that square right there. So d in terms of t equals, now you be careful here. A few people in the last test made a mistake when you did things like 12t squared. Laws of exponents, we have to square both factors. So that would be 144t squared. The radical first, and then I'll do that. I'm sorry, you guys. So let's clean that up. So the 12t squared is 144t squared. And then let's multiply 25 minus 16t times 25 minus 16t. And isn't 25 times 25 625? And 25 times negative 16t would be negative 400t, and then I've got to do that again for a negative 800t. And negative 16 times negative 16 is 256, so I see a plus 256t squared. Now combine our like terms, and how many t squareds do we have right here? Looks like 400t squareds minus how many t's? Minus 800t plus 625. And there we have it right there. Beautiful. That is the distance in terms of time of the horse from the boat at any time t. Very cool. Now, what are we trying to do? I think we're trying to find the time when they are closest to each other. So let's see. Express the distance d between the horse and the boat as a function of the time t in hours afternoon. So we've answered that question completely. I bet you there's more on this slide. Yeah, now by hand, determine what the minimum distance is between the horse and the boat. So the first thing I would do is find the time when we are at a minimum. So I need to minimize d of t in terms of time right here. And do you guys see the quadratic under the radical? Well, wouldn't the minimum of this radical function be at the same time that the minimum of this parabola under the radical occurs? And you guys know how to find extrema by hand of a quadratic. Remember that x equals negative b over 2a? So t coordinate of the vertex is going to be t equals negative b over 2a. And that equals, now let's go back to our quadratic, negative b, well, b is negative 800. The opposite of negative 800 would be 800 over 2 times a, and the a is 400, so that's an 800. So this t equals 1. So all I have to do to find the minimum distance is plug a 1 into this expression right here. And I will know when the boat and the horse are the closest and how far that distance is. So I'm going to get out my calculator again, and I'm going to go, well, t's are 1, right? So let's just put this whole thing in, okay? So second square root of 400 times 1 squared would just be 400, minus 800 times 1 is 800, plus 625. So I have the square root of 400 minus 800 plus 625, and that equals 15. So what's the shortest distance between the horse and the boat? That would be, my friends, 15 kilometers. Okay? All right. I think we have one more problem to do here. I hope you're having as much fun as I'm having.
Hi, pardon the interruption. Any students here still needing the bus ride home, please report to the back area by the bus pickup. You can stay in the building, but we need you by the back stairs or the main stairs in the B building. The bus will be on its way shortly. Just need to get a head count of who's all here. Thank you.
So that was Mr. Myers right there, and I feel so bad because it is right now almost 4 o'clock, and our students got out at 2:10. And we have been short bus drivers and short buses, so there have been some freshmen hanging around campus for almost 2 hours to get picked up by a bus. It just breaks my heart. Okay, we need to support education, get more bus drivers, get more buses, and get these kids to and from school. Anyway, enough politics. Let's get back to our last problem right here. So, water flows into a conical tank. So the first thing I'm going to do is picture a cone, but I'm going to picture that cone upside down so water can flow into it. So here's my water. We're about to turn it on, and that water is going to flow into a conical tank. There it is right there. All right? And let's go ahead and put the dimensions of this tank. Well, this tank is 100 centimeters wide, so this diameter up here would be 100, but I'm more interested in the radius. So I'm going to say the radius of that base is 50, okay? And the height is 250. So this height right here is 250 centimeters. And this water, when I turn it on, is flowing at a rate of 40 cubic centimeters every second. So I might call that something like 40T right now. See if that's what I did. No, I'm just right now talking about the 40 cubic feet per second. That's okay, but I bet you eventually we're going to call that a 40T. Anyway, find the volume V of the water in the tank. So first thing we need to know is, let's visualize the water in the tank. So as this cone is filling up with water, wouldn't that look something like that right there? Oh, beautiful. All right, and I don't know this height, and I don't know this radius, so that's an R, and this is going to be height right there. Okay, as a function of the height. So there's my height right there. Okay. Represent H as a function of the time T that the water has been flowing into the empty tank. Okay, well, let's go to work right here. So volume in terms of H. Okay, so I'm just talking about the volume of water in terms of this height right here. So you got to go back to geometry again, and do you remember how to find the volume of a pyramid or a cone? That's right. That's going to be 1/3 area of the base times height. So, and then we're going to represent h as a function of t, but we'll do that in a moment. H of t equals. So I need volume in terms of height, and I need h in terms of t. So let's go to my hyperlink work right here, and let's find those. So I'm going to write the volume of water in this conical tank in terms of the radius of this water level right there and the height. And we just mentioned this. Volume of a cone is 1/3 area of the base times the height. Just like that. Remember, the volume of the cylinder was base times height, or any rectangular prism. If I've got a pyramid or a cone, it's going to be 1/3 of that volume. Okay. Oops, didn't mean to hit that. I'm sorry. Uh-oh, now I'm way off, but let me get back there because this has been way too good to mess up now. And, well, let's just start right here and get there, you guys. Man, I tell you what, you hit a wrong button around here and you're in a little trouble. So let's get there. I know where we were. There we are. And now let's get to this work over here. There we go. Okay, so volume then is going to be 1/3. And the base of this cone right here, well, that's a circle. Area of the base is pi times the radius squared. And then the height of that water is h. There it is right there. Okay. Now, I need v in terms of h was what the first question asked for. So I have to find a way to write this radius right here in terms of height. Okay? Well, you see this a lot in advanced mathematics. If you look inside this cone, I hope you see two right triangles that are the same shape. And we call those similar right triangles. And you know from geometry, notice how we always go back to geometry? Similar parts of, well, I should say corresponding parts of similar geometric figures are proportional. Man, it's been a long time since I did that theorem. Anyway, let's draw the picture. So I'm going to draw the two right triangles so you can see them right out here like this. So you see the larger right triangle, the whole cone, and then the smaller right triangle is the right triangle down here, which is the same shape as the big cone. It's just smaller. And now let's put in our dimensions. Okay, so you agree that this dimension is 50 and this dimension is 250. And then in our smaller right triangle, we've got an R to H, just like that. Okay, now, if corresponding parts are proportional, let's write a proportion. And could I say that, boom, R to H right here would have to be equal 50 to 250, which I'm going to write as 1/5. And now, let's just solve for that R. So let's multiply both sides by H, and I'm going to get R equals, you could write that 1/5 H or H over 5, however you prefer. I like the H over 5. Okay, now let's take our volume formula up here, which is in terms of R and H, and let's write that in terms of only H. So V of H equals 1/3 pi, and then this radius right here, I'm going to put as an H over 5, right there. And now let's simplify that. So volume in terms of only H would be, well, look at this carefully. Do you see you have a pi and an H squared times H in your numerator? I'm going to write that as pi H cubed. All right. Now, be careful with your laws of exponents. Don't we also have to square this 5 and then multiply by 3? 5 squared is 25 times 3, that's a 75. So we've answered the first question. Volume in terms of H is pi H cubed over 75. And that's the volume of water in that cone. Beautiful. Now, they also asked us for an H in terms of T, the height of that water in terms of time. So this is the key moment right here. Remember they told us that water was flowing at 40 cubic centimeters every second? So the volume of water in that cone after I turn on the water, use the volume after t seconds to write H in terms of T. Okay, so Volume then is going to be, well, volume is going to be 40 times the number of seconds, 40t, and that has to equal this pi h cubed over 75. Okay, and now we want to write h in terms of t, the height of that water in terms of time. So all I'm going to do is have to solve this equation right here for this h. Okay, cool. H of t equals what? Well, looks like the first thing I'm going to do is get rid of that pi over 75. So I'm going to multiply both sides by 75 over pi. So 40t times 75 over pi has to equal h to the third power. And then what am I going to do to solve for h? I'm going to take the cube root of both sides. And with a cube root, I don't need a plus or a minus. So I'm going to say h in terms of t is the cube root of, well, I have in my numerator right here, 40 times 75. What's 40 times 75? I better punch that out. 40 times 75. And that's going to be 3,000. So I see a 3,000 and then times t over, and what do I have in my divisor? Just that pi. And there is my h in terms of t. And my friends, I believe we've answered both questions. Let's double check. Yeah, I need volume in terms of h and h in terms of t. Let's go back here. Volume in terms of h is pi h cubed over 75. H in terms of t is the cube root of 3,000t divided by pi. Wonderful. Okay, so your homework for this section is section 4.7. I'd like you guys to do 1 through 25 every other odd. Thank you for being here. I hope you enjoyed this video, and I hope you enjoy it when we go over this stuff in class. Have a great evening. Bye-bye.